Okay, as I was going over the lab with Sally today, I realized that I'm going to have to do some lecturing before we can do the lab. And so there won't be the hypothesis test portion of the lab today, which will keep the lab very, very short in exchange for the over-hour lecture we're about to receive. So, starting off, waves and energy transport. A wave is an oscillation that transports energy. It doesn't move something from point A to point B, but it moves energy from point A to point B. So a simple example is my voice. I'm up here talking, and the molecules of air that are coming out of my mouth are not the molecules that are coming into your ear. But the energy that's coming out of my mouth is being distributed throughout, and some of that energy is going into everybody's ears, and that's what they're perceiving as the sound. So, of course, sound is an example wave. It's transporting energy, but not actually moving. The examples shown here, the pitcher throwing the ball, is energy being transported by the ball? I would say yes, because the pitcher does work on the ball and gives it kinetic energy. The ball then travels through the air and comes to the catcher, and it does work on the catcher. So it delivered energy to the catcher. But it's not a wave, because a wave wouldn't have the actual material transported. Right? The ball is the material and it was transported. If you have a string with waves on it, that string will have each piece of the string stays in roughly the same position. It just moves up and down. But the wave travels down the string, so the person at the other end receives energy from that string. But the part of the string, the actual matter that the person moving, that never got to the person at the other end that received the energy. So that's a way to differentiate from waves compared to what we've studied before. So, since waves transport energy, an important property about waves is the rate of energy transported per unit area, what we call the intensity. So the intensity is the energy per time, what we call the power, per unit of area. And so this P here is not pressure, that's power. The intensity is the power over the area. Now, we're not going to work with intensity today, but it's important to know that's the key thing. We'll learn a little bit more Wednesday, tomorrow, and then next semester. Now, two fundamental types of waves, and I totally forgot to bring my slinky in with me, so we won't shake a slinky here in class. We have first here a transverse wave. It's called a transverse wave because the motion of the wave, if I have this slinky, you see the person on your left is moving that slinky up and down. So the motion of the pieces of the slinky is up and down in that picture. But what direction is the wave traveling? It's going left to right. So it's traveling in a horizontal direction, but the actual motion of the particles is vertical. So the motion of the particles is perpendicular to the velocity. So the velocity is like that of the wave, but the motion of the particles is vertical. When the motion of the particles is perpendicular to the velocity, we call that a transverse wave. Examples of a transverse wave include, well, a wave on a string or an electromagnetic wave. The other fundamental type of wave is called a longitudinal wave. This here, we again have the same slinky, but now the person at the end is pulling it back, pushing it forward, pulling it back, pushing it forward. What direction does the wave travel in this case? Still left to right, still horizontally. What direction do the pieces of the slinky travel? Left to right. So now we have the motion is in the same direction as the velocity. That's how we define a longitudinal wave. Also notice here we have places where the slinky is stretched out and that's called a rarefaction. I believe the origin of that word is because if you look at each piece of the slinky as a molecule or a particle in the wave, the particles are relatively speaking rare. That is, their spacing between them is bigger, so that there's less of them per unit, in this case, length. Then you have the places where it's tight together, that's a compression. We're going to talk about that for our sound waves that we're doing in lab today. Sound waves are also longitudinal waves. They're waves where you have the sound coming out of my mouth. Obviously, I have air molecules coming out of my mouth this direction, right? They're not coming out of my mouth this way. So they're coming out this direction, and then the sound waves are going the same direction that those molecules were moving. So that's why sound wave is a longitudinal wave. How many people like to go to the beach? Out here, I could have asked how many people have never been to the beach, but I'm glad to see we have a good selection. I love to go to the beach. I love to play in the waves. It's not the same when you're big like I am now. I actually float, and it's a lot easier. Up until I, became a teacher, I didn't float. And so it took more work. But when you're playing in those waves, you probably notice, I saw Michaela has her hand up, or had. We're playing in the waves. If you're out there in the water and the wave is coming toward you, what happens to you? Before it comes to you, as it's coming toward you. You should get pulled into it. So you get pulled out to sea when that wave is coming toward you. And then what happens to you when the wave gets to you? Now let's assume it didn't break on you. You go up. And then after it passes, what direction do you go? Assuming you floated up, not that you went down underneath. Then you go after it. So when that wave is coming, your motion wasn't simple. You started in front by going this direction. But then when it got to you, you went up. And then afterward, you went down and forward. So you were doing, and I'll take my arrows off because it has pretty arrows there. You're doing rotational motion there. Is that transverse or longitudinal or something else? Something else. It can be modeled as a combination of a longitudinal wave and a transverse wave. So water waves are not just a simple wave. How do we get these complicated waves? It comes because we're at the interface between two materials. Down low, you can see the waves are just going one direction. But up high, you have this rotational motion. So water waves are combinations. So are seismic waves. Do you have a question? No. You have a question?
So do you land in the same spot in the ocean? Because is it literally a cycle like that?
Because I am always playing around and flapping and doing stupid things like, exposing my chest to be Superman and have the wave bounce off of me. Clearly no for me. If you watch a little piece of styrofoam that's floating, it should be relatively close to the same place after all said and done. As long as it didn't break, as long as it was rolling. Yeah. Seismic waves. Seismic waves have two fundamental types of waves. The P wave, P stands for pressure or primary. Both of those should have some meaning to you by the time we're done with this. Primary means, of course, first. It's the primary wave because if an earthquake happens, let's say in Omaha, the first wave we feel here in Lincoln is going to be the primary wave. It's the faster wave. The pressure term is because a sound wave is a pressure wave. What type of wave was a sound wave? Transverse or longitudinal? Longitudinal. So the pressure wave means it's a longitudinal wave, where you have pressure that's going through the material. Then we have the next one called the S wave, and that can also stand for two words. I better put them in the same order, shear or secondary. Shear means that the motion is perpendicular to the velocity. What is that in our vernacular? Transverse. So the shear wave is a transverse wave. The secondary means it's the second one to arrive. So it's the slower of the two waves. It's kind of nice that we can make words to get both ideas in there. Now, of course, if you're on the surface of the earth, which is where we happen to reside, then just like with a water wave, you can have combination waves. And so on surface waves, you can have love waves or Rayleigh waves, which have different combinations of the two. So when an earthquake comes, you can feel a rolling that goes forward and backward and up and down, or that goes side to side. There's lots of variations depending on the combinations of the transverse and shear waves. I think all of this is necessary for the lab, just in case you're wondering. The speed. Speed is an important property of a wave, and the speed depends on the material that the wave is going through. Now, a transverse wave can only go through a solid. It can't go through a liquid. You need to have something that has a shear modulus, that is, it can support shear. And so a transverse wave needs something that supports shear. It can't go through a liquid. That becomes important to us for things like understanding what's going on inside the earth. We study seismic waves, and seismic waves show us that if there's an earthquake here, there will be a region from here to here that has no S waves. And that tells us there must be something inside here that's liquid, so the S waves can't travel through it. Oh, honey. I have it in here so my wife... she's not here. It's my wife's phone, not mine. Excellent. Hopefully she comes and picks it up. Oh, she's where?
Out there.
This side. There she is. Thank you very much, Tisha, for setting me straight there. She got somebody to open my office. I didn't leave it in there because I figured she wouldn't be able to get in there. Okay, so moving on. So the shear wave can't go through a liquid. And for a transverse wave, a shear wave, the speed is actually found by taking the square root of the shear modulus divided by the density. And that's going to come up on a later slide. Right now, I'm just focusing on the speed of a wave on a string. We do the wave on a string before we do the sound wave because it helps us to understand the sound wave better. So the speed of a wave on a string, that shear modulus, well, there's not really shear modulus for a string. We have to do something that kind of shows us what the shear modulus would be. And it turns out that the wave on a string, its speed is the square root of the tension in the string, that F is the force of tension in the string, divided by mu is the linear mass density, the mass per unit length of the string. Now we can think about this. I'm sure there are a number of people in here who play string musical instruments. The string musical instruments has different types of strings. Some strings are thicker than others. Why would you want to have strings thicker than others? So you can have similar tensions for different speeds. As we'll learn later, the speed is very important to the note that's going to be played by the string. And so having a thicker string, looking at that equation, what happens to the wave speed if you have a thicker string, one that has a higher mass per unit length? It slows down. So if you want a slower speed, you use the thicker string. If you want a faster speed, you use the thinner string. And of course, when you're tuning your instrument, you don't have a fine gradation of thickness of strings and choose the right thickness for the note. What do you do to adjust the tuning of a stringed instrument? You do what? Okay, change the tension. You tighten or loosen it. If you tighten it, you're increasing the speed. If you loosen it, you're decreasing the speed. So that's why we use that to adjust the pitch. My heart rate is just about slowed down from that pinging that scared me to death here. Important things about waves. A wave can be a pulse. In fact, I'm going to show in just a moment a pulse, a single pulse of a wave traveling down a string. Or it can be a periodic wave, something that repeats over and over and over. If you are playing your flute, your trombone, your euphonium, that's what the cool people play, or your violin, in all cases you have a periodic wave. You have a wave that's repeating over and over and over. And so we have terms we need to know to be able to identify these. So these terms include those words: period, frequency, wavelength, and amplitude. So we're going to go through these words, obviously like everything today, in rapid fashion. First, the period. The period is the time for something to repeat. So for instance, the period for my church going is weekly. I go to church once a week, every Sabbath, right? So, period, the time for something to repeat. What's the period for the Earth's orbit around the sun? 1 year. Or in days, that's 365.2422 days. Right, that's the period. Once you got that, that's a simple idea. The frequency is how often it occurs. So since I said I go to church, the period is 1 week, then the frequency is once per week. Right, the frequency is how often it occurs. So since the period is the time for between something occurring, and the frequency is how many times it occurs per unit time, the relationship between the two is very, very simple. Frequency is 1 divided by period. Question?
I'm kind of confused. Why wouldn't the period be like an hour and a half, and then the frequency would be weekly?
Because the period is the time for it to repeat, not the duration of, in this case, the church service, but the time from one church service to the next church service. That's the time for it to repeat. It's important to get that straight. That's a good question. In terms of units, for period, we're measuring time. The SI unit of time is seconds. So seconds would be the SI unit for period. If we're talking about the period for the Earth's orbit around the sun, we're much more likely to use the mean solar, well, we don't have to say mean solar, the year. Mean solar days. You know, days have different lengths. You probably know that, right? And so the mean solar day is 24 hours. Any given day could be something different. Frequency then would be 1 divided by seconds. And we have a special name for 1 divided by seconds, just like we have a special name for a kilogram times a meter per second squared. 1 divided by second is called a hertz. Remember, raised to the minus 1 means 1 over. So 1 hertz is equal to 1 over 1 second. So when we talk about frequencies, we very often say, you know, that's 10 hertz, 1,000 hertz, 104.5 megahertz. Mega means, of course, million. So that's the frequency. Then we have the wavelength. I'm going to write here, period was the time to repeat. The wavelength is the distance to repeat. Now, if I'm talking about a simple pendulum, something that's going like this back and forth, it's not traveling. So it's not a wave. And it doesn't have a wavelength because it doesn't have a distance to repeat. It still has a time to repeat. It still has a period. It's oscillating. But it doesn't have a distance to repeat. But if I have a wave that's traveling by me, there is a certain distance for it to repeat. Now, waves can have all kinds of shapes. For instance, you could have a wave that is shaped like this. It exists. We can make them. We're not going to discuss them in physics class. What we will only talk about is simple, I can change colors for this because it's such a keen point. Simple harmonic waves. Simple harmonic waves are waves that are sinusoidal. A sinusoid looks like that. A sine wave would start here. A cosine wave looks exactly the same. It just starts there. So both the sine wave and a cosine wave are sinusoidal. Some people get confused and say, well, shouldn't that other one be cosinusoidal? No, it's still sinusoidal. So we're going to limit ourselves to simple harmonic waves. Now for the simple harmonic wave, I said that the wavelength is the distance for it to repeat. So if I have my axes here, so I have position on this axis, and my last word here, almost, displacement on the vertical axis. I have a nice graph of my motion. Now I have to specify what these words amplitude, displacement mean before I can go on with that graph. Displacement means how far something has moved away from its equilibrium position. So for instance, if you have a string instrument, that string's equilibrium position is just a straight string, right? It's pulled tight enough, it should just be straight. If you look at a single piece of that string, when you pluck it, it's going to move up or down from that straight line. And the displacement is at any instant how far away it is from the equilibrium position of the straight line. And the amplitude is simply the maximum displacement. So amplitude is the farthest it will ever get from the equilibrium position, the largest displacement. Displacement. Good enough. So now with my picture I've drawn of a wave. A wavelength is the distance for it to repeat. Well, I drew my cosine there starting with the green. In terms of the displacement, what's the displacement where I drew my green line? Is it 0? Is it about half of maximum? Is it full maximum? Is it negative half maximum, negative full maximum? What would it be? It's at the what? Maximum. What do we call the maximum displacement? Amplitude. So I'm at its maximum now. This is the amplitude. If it's going to repeat, the next place it's going to repeat is when it comes back up to that maximum amplitude. So that would be here. So this is the wavelength, and we use the Greek L, lambda, for wavelength. Now, it's easy if you use the peak where it was at maximum value. Some people can get confused. What if, instead of choosing the peak position, I had chosen this position here for starting? What's the displacement at that point? 0. So if I go forward, where do I get the next displacement of 0? Half a wavelength away. How is it that I have the same displacement and it's not a full wavelength? It's what?
Where you're just going from like a node to a node to a node.
Actually, node only applies if you're talking about a standing wave. I know what you mean.
Yeah.
For a wavelength that needs to repeat, that doesn't mean just have the same position, it also needs to have the same velocity. At this point here, we had a downward slope. Here we had an upward slope. They're not going to be the same velocity. So we have to go to the next place where it has the same slope and position for it to be one wavelength. Now, I do have better pictures coming up. Ones that aren't my crazy drawings. So here we can see a nicely drawn wave. It calls it a crest at its maximum, a trough at its minimum. It has A marked here. What would that A stand for? The amplitude. And how do you know that's the amplitude? It's the farthest it gets from the equilibrium. They mark this as y. What would have been a better term to use rather than y? Displacement. And on this axis, they just marked x. That would be the position of your wave. Relationship between these things. The wavelength is the distance that it takes to repeat. The period is the time that it takes to repeat. What's the relationship between distance and time? Speed is equal to distance over time. So if I take the distance it takes to repeat and divide it by the time it takes to repeat, the distance we call the wavelength, the time we call the period, and so I have my relationship that says the speed is the wavelength divided by the period. And since frequency was 1 divided by the period, right, they were just inverse of each other, I can also write that as speed is frequency times wavelength. That's one of the equations we're using in today's lab, relating the speed, the wavelength, and the frequency. Now this here, technically I didn't have to cover today, but I thought it was interesting to note the speed for water waves. It depends on if it's a deep water wave or a shallow water wave. So a shallow water wave, the speed turns out to be basically 313 meters per second times the square root of the depth per meter. It says per meter. You just put in the depth in meters, and then that's a unit meter that's going to cancel. So that's for a shallow water wave, For a deep water wave, it's 1.25 meters per second times the square root of the wavelength. And now here's a good question for you. What's the definition of a shallow water wave versus a deep water wave? And the differentiation is if the water is deeper than a half wavelength, then it's going to be a deep water wave. If the water is less than half a wavelength, it's a shallow water wave. How deep is the ocean? Was it you guys? It must have been my other class where I had that as a Flip Friday question. No, I think it was this group. I don't know. The typical depth of the ocean is around 2 miles. Yes, the ocean tends to be deep. Not the beach, mind you, the ocean. So when we have waves going through the ocean, I didn't load up this video, but it's pretty cool. It shows you a tsunami, the tsunami that occurred in 2004 actually, and how it propagated across the ocean. And the question here is the tsunami a deep water wave or a shallow wave? You can't tell from this here. I'd have to show you the graphic, and given time, I'm not going to show you. What do you think it is? This is also not an active clicker question. Don't worry about getting out the clickers. What do you suppose it is? How many people think, by show of hands, that a tsunami is a shallow water wave? Okay, I got 6-ish. How many people think it's a deep water wave? Okay, I got about 12. That's most of you. The fact is, a tsunami is a shallow water wave. And you're like, you're kidding, right? You just said the ocean is 2 miles deep. How can it be a shallow water wave in a 2 mile deep ocean? Well, that means the wavelength must be more than 4 meters long. Tsunamis have very long wavelengths. Now, in America, I grew up calling these things tidal waves. The name tidal wave is completely out of vogue with scientists. They don't want us to use it. The reason is simple. Because tidal waves imply that it has something to do with tide. And tidal waves have nothing whatsoever to do with tide. Now, the Japanese word tsunami means a harbor wave. And the harbor wave is kind of indicative of what's going on. You have a wave traveling through the ocean. The wave has a very high speed because, well, we just come back here to the shallow water wave. We take that 2 miles or 3 point whatever kilometers, 3,000 something meters, square root it, multiply 313. We get a pretty good speed for the wave. it's really traveling. Now, what is this is a pressure wave, right? The water going into the water, it's going to be mostly pressure wave. What is happening is that wave is traveling through the water. What do waves do? They transport energy. So we have energy transport. What's happening is when the wave comes, the stuff in front is basically still, the wave hits it, transfers momentum, and now the particles start moving with a constant speed. So behind the wave, you have a whole ocean that's now moving toward you. In front of it, you have a stationary ocean. When you're going through the deep ocean, a tsunami might stand up a couple inches. So it's not like you see this giant wave coming toward you. But an airplane flying overhead can see a tsunami. They can see it because you have ripples on the ocean, and when that wave hits, it compresses things so the ripples are much steeper. And so it looks like there's a shadow because you have the sunlight more reflected away instead of reflected back up toward you. So it looks like a shadow where the tsunami is passing. When the tsunami gets to shallower water, it's transporting energy. That energy was making a whole bunch of water move. When you get to shallower water, where's that energy going to go? It's going to go up. It's going to make it start stacking up. So you have this small wave traveling through the ocean. When it gets to the shallow water, for conservation of energy, it starts being really tall. And so that's why the harbor wave is an apt term, because it's a small wave until it gets to shallow water, like in a harbor, and then all of a sudden it grows really big. If you've ever watched videos of a tsunami, and I never did until a tsunami hit my childhood home of Santa Cruz. It was a really minimal tsunami, and you're like, even in the harbor, it's like a foot tall. I'm like, I play in foot tall waves all the time. This is no big deal. That's what the people who were watching thought too. But the difference is, in a normal wave, as we talked about, it pulls you out when it comes toward you, lifts you up, and then you follow it after and get back to about where you started. Here you have a whole bunch of water that just keeps on moving. So the wave hits you, and it just keeps going. And so things get dragged behind it, and it's much more devastating than a normal wave of the same height would have been. So I throw that in because I find it extremely interesting, and of course, it's the physics we're doing, so we should learn about it. Harmonic waves. Remember I said we're going to limit ourselves to simple harmonic waves. Harmonic waves, sine or cosine, we have the speed, the maximum speed for a particle moving up and down turns out to just be the angular frequency. Omega is equal to 2 pi times the regular frequency. What do you suppose the units are for omega? Radians per second. Now, once again, a radian is unitless, but you have to say radians per second so you don't get it confused with hertz. So the maximum speed is the angular frequency multiplied by the amplitude A, and the maximum acceleration is that angular frequency squared multiplied by the amplitude A. Some very simple relationships in calculus. You just take a first derivative, that's what brings out the omega from sine or cosine. Second derivative, bring out another one. It's very easy to see where that comes from. This equation, you don't need to know this equation, but it's interesting to note the intensity of a simple harmonic wave on a string, actually, it doesn't have to be on a string, is proportional to the amplitude squared times the frequency squared. So the energy transported per unit area per time depends on the amplitude squared, so bigger wave, double the amplitude, 4 times the energy, and the frequency, double the frequency, 4 times the energy. So here is a pulse. I just said simple harmonic waves are harmonic waves, and now I show you a wave pulse, not a harmonic wave. What I'm going to do here is talk about how we describe a wave. So I have this pulse that travels with some speed v. And if it's just a pulse, I could talk about the position of the pulse. The position of pulse would be, the speed of the wave multiplied by time. And it turns out that the displacement, now this y is the displacement, is going to be a function of if the wave is there or not. So since x is equal to vt, then I'm taking this here, t minus xv, or x over v, if I divide everything by v. Then I have, if I move this across, well, I'm going to write this whole thing out very, very carefully. X is equal to x0 plus vt. And so if I divide everything by v, then I will have this thing right here is x0 over v is equal to, well, backward. x0 over v is x over v, a constant, minus t. Oh wait, x over v is not a constant. It's the x0 over v that's a constant. And so that's what is inside there. It's saying the height is a function of what your position is, and that position travels with the wave. Okay, probably a little confusing there, so let's go to better descriptions. For a sinusoidal wave, you can use either sine or cosine. Both of them are sinusoidal functions. They both give you the same shape. So the top equation shows the displacement as a function of position and time is equal to the amplitude, the maximum displacement, times cosine of the angular frequency multiplied by something that would be starting position. As time changes, if x stays constant, then that's going to be a cosine omega t with a constant, plus a phase angle. If time stays constant and x is allowed to change, then it's cosine of minus x omega over v plus a constant. So it allows you to both consider how it travels with time and how it varies at one location, how it travels with position, how it varies at one location with time. All of these equations would describe a traveling wave. These top two would describe a wave traveling to the right. The bottom two would be describing a wave traveling to the left. What's different between the upper two compared to the bottom two? The minus and the plus. The upper one, omega t minus kx. If those signs are opposite, then to keep this thing here, this argument constant, as time goes up, x must go down. This one here, they're both positive as time goes up. Actually, no, I said that wrong. To keep this constant, as time goes up, x must go up. So this has x increases as time increases to remain constant. And so that's why it's going to the right. X increases, we consider that to the right. The lower one is just the opposite. As time increases, x is going to have to decrease to keep it constant argument, so it's going to the left. So all you need to do when you look at one of these equations to determine if it's going to the left or to the right is, do the two terms have the same sign? If they both have the same sign, it's to the left. If they have opposite signs, doesn't matter which one's positive and which one's negative, if they have opposite signs, it's traveling to the right. Notice cosine and sine. The only difference that makes is what the displacement is at time equals 0. Finally, a lot of people well, that was a bad choice of color there. A lot of people, especially in chemistry class, have learned about things called wave numbers. The wave number is actually a number that tells you the wavelength. The wave number is the angular velocity divided by the speed at which the wave is traveling. And when you use your relationship between omega and frequency, omega is 2 pi f, and then between frequency and wave speed and wavelength, that simplifies to the wave number is equal to 2 pi divided by the wavelength. So when you're using spectroscopy, if you're doing something like IR spectroscopy, I think it's standard to use wave numbers to describe the wave. Using a wave number in something like inverse centimeters. That's just another way of telling you what the wavelength is. And since you're talking about light waves, that's also telling you the frequency because the speed of light in vacuum is constant. So, notice the difference in these graphs. There is an obvious difference and a more subtle difference. What's the first difference you see? Okay, the opposite. That's the obvious difference. One is going up, the other one's going down, both starting at 0. What's the more subtle difference? One of them's x and one of them's t. This one here is taken at one moment. For this case, it was time equals 0. And my professor in graduate school called that a snapshot. Because if you were to take a photograph of the wave, that's what you would see on the photograph. Now, the other one is taken at one location. In this case, that's at x equals 0. And of course, that's not what a camera would see, so I don't have a simple term for that. These are two different ways of looking at the wave. One is looking at how it travels. The other one's looking at how something changes as the wave is passing. Both of these are useful, and we need to be able to understand both of them. For today's experiment, we're going to be using this way. Okay. Now this here has a question with it. I took out the question, at least I think I did. But I want us to try to understand some basic things about the wave. Now, is this the snapshot or the other one? It's the other one, because this is the one that's changing time. Now I have a particle that moves up and down. At what time is the particle momentarily not moving? At the crest. At the crest, it's momentarily not moving. It's just like if I throw a ball up. It goes up, so the position is going up, gets to the top, momentarily comes to rest, then comes back down. We learned about this the third lab, when we learned that the slope of a position versus time graph gives us the speed. Now, this is the speed of the particle moving, not the speed of the wave. So here I have a speed of 0. Here I also have a speed of 0 because it went to its bottom and then started coming up. So here I have a speed of 0. So I put my speeds where there's 0 in green. Based on the slope, how can you determine if it's going up or going down? Going back to those labs, the second and third labs. Okay, if the slope is negative, it's going down, it has a negative velocity. If the slope is positive, it's going up, it has a positive velocity. So this portion from here to here has a negative velocity. But from here to here, it's going to be positive. How do I find the maximum velocity? Where the slope is the steepest. So with the sinusoid, it turns out that that's at the center. So the velocity is a maximum there, a minimum here, a maximum here. So now I can draw in what the velocity looks like as a function of time. That is, it's going, forgive my poor sinusoid here. So that's what the velocity looks like as a function of time. Now, if I want to find the acceleration, what do you find the acceleration from? The second derivative, which was from looking at the slope of the velocity graph. That was like labs 2 and 3 where we looked at that. Or not 2 and 3, 3 and 4, the next. 3 was looking at both. So if I look at this one, I could say, well, I am going to have 0 acceleration here. That's a negative slope, so it's going to be negative acceleration until I get to this point where it's going to be back to 0. Then it's going to be positive. Here I'm going to have maximum negative acceleration. So my acceleration is going to do something like so I can plot my acceleration and my velocity as a function of time just by looking at that position as a function of time and using what I know about velocity and acceleration relative to position. So stuff that we learned at the very beginning of the semester, coming back, something we need to pay attention to again. Now, the principle of superposition is an easy concept, but it's kind of hard to actually see it fit together. So the principle is, if I have two waves and they hit each other, they pass through each other. Now, contrast that to me hitting Reagan. If Reagan and I run toward each other and we hit each other, we're going to bounce off each other, right? But if we were waves of reasonably small amplitude, large amplitude waves, this doesn't work out right. But if we were waves and we ran toward each other, we just passed through each other. And so once I got past him, you'd see there's me, you'd see there's him. No differences. While we're going through each other is when the interesting stuff happens. While we're going through each other, if we're waves, we simply add together. And so while we're going through each other, it wouldn't be there's Richard and there's Reagan, it'd be there's the Richard Reagan monster, right? Waves do the same thing. Now keep in mind it's only for small amplitudes. But here's pictures to illustrate it. So here are two pulses heading toward each other. They hit each other because both pulses are positive. They add to make an even taller wave. The height doubles when the two are right on top of each other. But then they just pass through each other. So this pulse looks just like that pulse. And likewise, this pulse and this pulse look the same. They pass through each other unfazed, but while they're going through each other, they added up. Now we call this here, when they add up to make something bigger, constructive interference. And we should write that somewhere where we have enough room for the whole word. Constructive because they add up to something bigger. I don't remember if I have a slide for destructive interference. Nope, I don't. So let me just show the reverse. Let us suppose that I have one pulse that's like this, going that direction, and I have another pulse like this going this direction. When they meet each other, so that they're right on top of each other, how are they going to add? I tried to make them exactly alike, just one upside down of the other. And so if they're right on top of each other, they would add up to 0. So I have a string and I have two pulses going opposite directions. When they meet each other, the string is momentarily completely flat. Then it goes from completely flat to having the red one continue on the way it was going and the blue one continue on the way it was going. Now remember, we talked about the intensity had to do with the amplitude. Well, when it's completely flat, what's the amplitude? 0. And so it seems like we lost all the energy, right? But we didn't. What we lost was the energy that was in displacement, but that energy had to go somewhere. Physics says it can't be made or destroyed. So where do you think that energy went? Well, let's look at what's going on with the wave. If I look here at this pulse, on the front side, what's happening to the string? As the wave comes, it's being lifted up. So I have, the string has an upward velocity. There's kinetic energy in that upward velocity. What's happening on the backside? It's going down. So you have kinetic energy on both sides due to the motion of the string. Now, when I have these meet together to make a flat string, this here was coming up, this was coming down, and what you have is very high speeds. It's just momentarily flat while we have very high speeds going like this. And so those speeds then make it so the amplitude comes back after they pass through each other. So we basically converted the energy that was in the displacement into kinetic energy, and then it comes back into displacement after they pass through each other. So this here would be destructive interference. Once again, that is a highly important aspect of a standing wave, what we're saying in lab today. The last thing we really need to know before we can get to the specifics of what we're doing in lab is what happens when a wave reflects. When a wave reflects off of a non-moving barrier, when the wave gets here, what is the string doing to the support when the string is going up from the support? The string is pulling it up. And so the support is doing what to the string? It's pulling it down. So the support is pulling the string down because the string is pulling it up. Well, that downward force is going to result in the reflection having a downward pulse. This downward pulse came because of the downward force the support had to make to hold the string in place. So I have a wave will invert, it will flip the side of the amplitude when it reflects off of something that's a fixed barrier. Does that make a reasonable sense? What if instead of being a fixed barrier, it was attached to nothing? I don't have a picture for that, I don't think. What if it was attached to nothing? What force would the nothing put on the string? That was a really silly question, right? Nothing. So the string would have nothing to stop it from going up. Now normally the other string there is keeping it from going up. Right? The other string there is pulling it back down. Well, if we don't have anything there, it just keeps flying up. It has momentum upward. And so that upward momentum means that if I have a pulse that looks just like, I can kind of do it. That's the wrong tool. So I have these pulses now, but instead of having a support, they're now free. What's going to happen is, with the next line, it's going to go and still going like this, and then it's going to be like this reflected back. And so I'll end up with a pulse like this reflected back if it's tied to nothing. So the reflected wave comes back the same if it's tied to nothing, but comes back inverted if it's tied to something that can't move. What if it's tied to something that could move? What if I have a thick string tied to a thin string? If the wave is coming down to the thick string, the thin string is so light it's like there's nothing there. So if it's a thinner string, it's going to come back as if there's nothing there. So it'll come back the same. If you have the wave coming down the thick string and hitting the thin string and hitting the thick string provides a big impedance, as we say, and it acts like a barrier and it inverts. So when you have two strings tied together, if the wave starts on the thinner string, it's going to reflect inverted. If it starts on the thicker string, it reflects the same. Those rules can be a little bit confusing, but once again, they play an important role in today's lab. The frequency does not change. The frequency is going to be the same. This is really easy to explain. If I have two strings of different thicknesses and thus different speeds tied together, if I had a different frequency on one string than the other, then they would have to break apart. For that knot to stay held together, the knot has to go up and down at the same frequency on both sides of the knot. So the frequency of a wave simply cannot change when it goes from one material to another. Of course, if the speed changes and the frequency doesn't, what does that tell you about the wavelength? Wavelength is equal to the speed divided by the frequency. If the frequency stays the same and the speed increases, what's going to happen to the wavelength? It's going to also increase. Right? So the wavelength changes when you go from one material to another, but the frequency can't. We'll learn second semester about the wave-particle duality of light, and that's one of the things that we look to there. So this is just what I was doing. The frequency stays the same. So, interference with two traveling waves. If I have two waves that are traveling together, both going the same direction, then I can just use what we learned about interference, and the two waves will have their amplitudes add up. Reasonably simple. And if the waves are both in phase, as we say, that is, they reach their peaks at the same place, then we'll have constructive interference. If I had the two waves, this is just saying the amplitudes, the sum of the amplitudes of the two individual waves. If I had two waves that are out of phase, so one's going up when the other one's going down, our superposition principle says that we still add up the displacements. And so the total amplitude, if they're exactly out of phase, is going to be the difference in the two. And so we had here destructive, not completely destructive because the amplitudes weren't exactly the same, but destructive interference by having two waves that were out of phase traveling together, they added up to a much smaller wave. Now, go ahead.
With destructive interference, does that cause greater strain on the medium? So if you had a rope or whatever and you had two waves traveling opposite of each other, when they met, would it be possible to have the waves such that when they met, it would actually break the rope?
Well, if it's constructive interference, yeah, you could make it so it's too much. If it's destructive, no.
Okay.
Standing waves are the result of having two waves traveling in opposite directions with the same frequency. If I have two waves going in opposite directions with the same frequency, then, well, here we have mathematically, what direction is this top equation traveling? To the left. It's to the left because these have the same sign. This one here is to the right because they have opposite signs. So I have two waves traveling in opposite directions. If we plot those out, when you add them up, here is adding the two waves together. You have the same amplitude, and it said one had a positive A, blah, blah, blah. The other one was negative A, so that's why there's a minus sign in between. When you add those up, using that rule on the bottom for signs, for adding signs, you get this is equivalent to that. 2a cosine of omega t sine kx. Now what you notice here is this now has decoupled the time and the position. You don't have an equation that has something times t plus or minus something times x. You have an equation that's something times t multiplied by something times x. And so what we can do now is we can plot the time behavior separate from the position behavior. And what we're going to have is a wave that travels in between these points. Notice there are going to be positions where sine of kx is 0. That means as these two waves are traveling through each other, there will be positions where there is no displacement. And we call those positions where there's no displacement now a node. So we call this here a standing wave, standing because it appears to not move. What's really happening is we have two waves moving through each other, but it appears to not move, and these nodes are places where there's no motion at all, where the string is completely flat. And then we have the places where we have the maximum change, and those we call antinodes. Antinodes, it goes from a positive maximum down to a negative maximum, back up to a positive maximum. Oftentimes when we see these, you only have the top line and the bottom line, and you tend to think that the string is somehow split in two and is stationary. But it's not. It's going up and down between those, but at the nodes it's not moving. So this is what we call a standing wave. Missed. Got it. With this standing wave, it's important that we once again think about what a wavelength is. How far away from this antinode is one wavelength? What'd you say? One what? Yeah. How far do you have to go for it to be one wavelength? You go until it... Okay. Same position and same velocity. So we come and we follow this. Let's just follow this down. Comes down here. That's not the same position. Oftentimes people think that's a wavelength, but that's not. That's half a wavelength. And you have to come up to here again. And so that's the wavelength. So the wavelength is the separation between two antinodes, not adjacent ones, but one that's two away. Or likewise, the wavelength would be going from here to there. So this is setting up a standing wave. What we're going to be studying is standing waves. So I'm going to come back to this picture as we start zeroing in on the standing waves in a tube. To make standing waves, let me be a little specific here. Let us suppose that I have a string. And the string is tied to two supports that are separated by a distance L. If I'm going to set up a standing wave, since the string is tied to the supports, how much motion am I going to have at the two ends of the string? None. So if I set up a standing wave, what do we call the points with no motion? We call them nodes. So I'm going to have a node here and a node here. Now if we look at this picture, I can see my options. One option would be this could be one end of the string and this could be the other. In that case, how many wavelengths would I have on the string? Half of one. So I could have length is equal to 1/2 wavelength. But I could also have gone from here to here. How many wavelengths would that be going from one node to the other node? A full wavelength. So I could have also had length is equal to, and I'm going to put 2 divided by 2 wavelengths. Obviously, that's a provocative way of writing it. And then for this picture, the third and final option would be having here is one side and here's the other. How many wavelengths do I have there? 3 halves. And so I have L is equal to 3 halves wavelengths. Well, we can see right away there's a simple relationship. The length of my string must be equal to n over 2 wavelengths long. I'm going to take this and solve it for wavelength. I'm going to say, okay, the wavelength that will resonate on the string, I'm going to put a subscript n for each wavelength that resonates on the string, must be equal to 2L over n, where n is any integer. Because notice I had 1 half, 2 halves, 3 halves, so n was just integers there in my problem. So this tells me the wavelengths that will resonate on the string. Now, we know that frequency is equal to speed divided by wavelength. So if I put subscript n's on each of these and then substitute that in, that's going to be v over 2L over n, which would be v over 2L times n, where n is again 1, 2, 3, etc. So these are the frequencies that resonate on a string. I'm going to write a little more carefully. F sub n is equal to v over 2L times n. N is equal to 1, 2, 3, etc. Now we can relate this directly to tuning a violin. When I'm tuning that violin, I'm trying to get the right frequency. And if my frequency is too low, what do I need to increase? The length I can't change, so what do I need to increase? I need to increase the speed to increase the frequency. But we saw that the speed was given by the relationship V is equal to the square root of the force of tension divided by the mass per unit length. So if I increase the tension, that will increase the speed and thereby increase the frequency. So now we can see why we tune the way we do with a stringed instrument. And now I'll have a pretty picture to go along with the calculation I just did. Actually, no pretty picture here. This is all the work I just did. For n equals 1, it's called the fundamental because that's the lowest frequency it will resonate at. That's the one that you tune to. You tune the fundamental. Come on, next slide. I've already gone through everything we need that picture for. Right, the 1, 2, 3, etc. Now going to sound waves. We already talked about sound waves having compressions and rarefactions. With the sound wave, we can either talk about the pressure, that's where compressions and rarefactions come, or we can talk about the displacement of a molecule from its equilibrium position. So here in this picture, we have pressure plotted as a function of position. And you see places where we have the rarefaction, it's low pressure. Places where we have the compression is high pressure. And the pressure follows a sinusoidal pattern. Or I could plot the same data, or the same configuration, but now plot the displacement of a molecule from its equilibrium position. These molecules were normally equally distributed everywhere. And here the molecules are the same place. Here the molecules tend to have been moved to the right. Here, same place. Here tend to be moved to the left. And so we have the displacement. And one thing to note, pressure was the highest when I had those dots closest together. When the dots are closest together here, what's the displacement? 0. So those are what we say 90 degrees out of phase. When one is the maximum, the other is 0. That's a 90-degree difference for a sinusoidal wave. So the displacement is 90 degrees out of phase with the pressure wave. When we go through the waves, we can talk about either one, but it's important to remember they're out of phase. Just a little about sound waves. I tried to get rid of all these, but forgot. We can hear sound from about 20 hertz up to about 20 kilohertz. Our hearing varies in efficiency with pitches, and pitch corresponds to frequency. So a frequency of 20 hertz is a very low frequency, a very low pitch. A frequency of 20 kilohertz is a very high frequency, a very high pitch. Old folk like me probably can't hear up to 20 kilohertz anymore. I probably top out somewhere around 10 kilohertz. This graph here is showing how well we hear. A typical person hears best at somewhere around 3,000 hertz. And your hearing gets much, much worse if you get up much above 10,000 hertz, and it's pretty poor when you get down below 20 hertz. Now, just a shot out there. As I'm talking, or if I were to sing, what frequency range do you suppose I am talking or singing in? What?
Well, you have a pretty deep voice.
No, I don't.
Somewhere around 1,000. I've got.
Lower. We tend to be in the ballpark of a couple hundred hertz. Couple hundred for a guy, maybe 500 for a girl. Girls tend to have higher voices than boys. I heard a weight there. And yeah, I actually do have a high voice. I try to lower it a little bit. I'm like, I'm high voice Peyton Manning. That commercial actually bugs me because I like barbershop quartets. So we're not going to spend more time on this today, just to understand how frequency plays into things. The speed of a sound wave in air is going to depend on, now this is not a shear wave, it's a pressure wave. It's a longitudinal wave. The longitudinal wave, instead of being the square root of the shear modulus divided by density, it's the square root of the bulk modulus divided by density. Shear modulus had to do with shear stresses and strain. Bulk modulus has to do with compressive stresses and strain. Now, if you just look at this equation, you're like, that isn't going to help me much. But of course, the bulk modulus and the density of air are primarily dependent on temperature. And so it turns out that the speed of sound in air is primarily dependent on the temperature of the air. And so doing some simple wave fitting, this is a linear equation that works very well through a broad range of standard temperatures. Any temperature you have in a room is going to be well within that range. And it's good to within 1% accuracy in that range. So you can use that. Now our textbook or our lab guide has this equation as well as one that has a square root. They both give you the same answers. They're just different fits to the data. They both give you the same answers in the room temperature range. So you can use either one, but we can just calculate the speed of sound in air based on the temperature. So one of the things you're going to do in lab today, come up here to the front of the classroom and read the temperature. And then convert that temperature from Fahrenheit into Celsius and calculate the speed of sound in air from that temperature. We're getting right down to the end here. Here's some speeds of sound in different materials. And you'll notice air is on the low end for speed of sound. That's the speed of sound in air at 0 degrees Celsius. The speed of sound in helium, about 3 times faster than the speed of sound in air. That makes a difference when I have helium filling my voice box instead of air. The sound travels 3 times faster, and that makes the resonance 3 times higher frequency. So if I breathe in helium, my voice goes up in pitch by about a factor of 3 times the frequency. because of the faster speed of the gas. Now, not shown here is sulfur hexafluoride. Sulfur, yeah, I don't care. It's easier to put SFL6. Sulfur hexafluoride has a speed that's somewhere in the ballpark of 90 meters per second. That's really slow. So if you breathe in that sulfur hexafluoride, what's going to happen to your voice when you speak? It drops. It's really awesome. It got that awesome, low, mellow, very wide sounding voice. Now, when I was a youngin', my 5th grade teacher told me that if I breathed in too much helium from that helium balloon, my voice would be permanently changed to that high, squeaky voice. Now, what do you think Mrs. Coelho's goal was in saying this? To make me stop breathing the helium. What was the obvious outcome? Oh, I had to breathe a lot. Because how awesome would that be? I mean, when you're in 5th grade, whatever it was, I didn't take 6th grade, so I know it's 5th or 7th. When you're that age, it would just be awesome to be that freak with the weird voice all the time. Not so awesome when you get older. And it didn't work because it turned out she was absolutely wrong. It's not changing the physical dimensions of your voice box. Yeah.
So if elephants have low frequencies that are not within our hearing range, if we gave them helium, then we could hear them?
That is right. Good application. Let's go do that. We could probably get a grant. Okay. Is it safe to breathe in helium? Okay. Despite what you may or may not have read, there is no documented case of a problem with somebody not trying to kill themselves and breathing in helium. You might have read about a girl who went to a party and died and they blamed it on breathing helium. But the investigation did support that that was the reason she died. And there are cases of people dying from helium. Things like idiots taking a big helium balloon and pulling it down to his waist. Well, what happens then? You suffocate because you don't have enough oxygen to breathe. Right? So people have died from stupid things like that. But not from just breathing in from a helium balloon. Yeah.
Well, they spray stuff inside of it for like elasticity. It'll make the solution last longer, so maybe they breathe in the chemicals.
I didn't know about that. I know it is disappointing that the helium does usually go through the wall of your balloon. Okay, sulfur hexafluoride. Is it safe? You probably don't know anything about sulfur hexafluoride, right? Well, helium is lighter than air. You do know that. So as long as you're standing up, the helium's going to tempt you. Just come on up out of your lungs. Sulfur hexafluoride is more dense than air. So where's the sulfur hexafluoride going to settle? The bottom of your lungs. So if you're shallow breathing, your lungs could have, still have sulfur hexafluoride, which means you're getting less oxygen. When I used sulfur hexafluoride for a class, I, did my little thing. I sang, and an octave lower. It was really awesome. And then I was talking normally, and then I said something loud. And that's all good teachers do when I speak loud. I use my diaphragm, force that air up out of the bottom part of my lungs, and also my voice dropped again. Which was hilarious. There is more danger with the sulfur hexafluoride because it will settle in your lungs and won't come out. Unless, of course, you stand on your head while you do it. Then you're just as safe as you would be with helium. And don't stand on your head when you're doing helium for the same reason. Okay, moving on. You might notice that we are getting to the very end of these. Now we get to tubes.
What if you take a little bit of helium and a little bit of sulfur hexafluoride? You wind up about the same?
Probably. Not much point in that, though, is there? Okay, here's an open tube. Open tube is open on both ends. So sound waves can freely come in, freely go out. What do you suppose the pressure is on each end of an open tube? Atmospheric pressure. So if we set up a standing wave, which is the only context in which the words notes and antinodes have meaning, what do I have at the ends of the tube for pressure? It's constant, and if it's constant, that must be a node. So for an open tube, I'm going to have a pressure node on both sides. Now I can also talk about displacement. Air can move freely in and out of the tube. It turns out that makes the ends of the tubes displacement antinodes. So I either have displacement antinodes at both ends or displacement nodes at both ends. Well, with a wave on a string, what did I have at both ends of the string? A node. So if I talk about pressure, the open tube is going to have all of the exact same calculations I did. Pressing my And so the work I already did to find the resonance for an open tube is exactly the same as finding the resonance, or excuse me, for a string is exactly the same as the open tube. So you'll see here everything just like I did. We have the graphs here of pressure that look just like the graphs we did for the wave on a string. Here we have the graphs of displacement that look the opposite. Now, this is a closed tube. I'm going to dump out the water. It's a closed tube. How many sides is it closed on? One. If it's closed on both sides, we don't call it a musical instrument anymore, because it doesn't have a place for the sound to come out. So a closed tube is closed on one side and open on the other. So in terms of pressure, what do we have on this side? A node, because it's going to be atmospheric pressure. On this side, it can have whatever pressure it wants, right? Because it's just got a wall there. So on this side, the pressure can be anything provided it doesn't break it. That turns out to be then a pressure antinode. So for the closed tube, you have, go to the next slide. Actually, probably 2 slides past here. For the closed tube, you have a pressure node on one side and a pressure antinode on the other side. So when you look at the equations, or look at the graphs, because I like to do the graphs here on your right show the pressure relationships, and the shortest wavelength that will resonate is going from a node to an antinode if you're looking at displacement, or an antinode to a node if you're looking at pressure. How many wavelengths long is this? That's 1/4 wavelength. Perfect choice of colors. The contrast is outstanding. So 1/4 wavelength. Now going to the next node on one end to antinode at the other, how many wavelengths long is this? It's 3/4. It's 1/4 from here to here, and then 1/2 from here to here, put them together. And we call this L3 is equal to 3/4 wavelengths. And then the next one, there's a full wavelength plus 1/4. So I have L5 is equal to 5/4 wavelengths. Putting those in, you can see over here, I have those equations already written. Put them into a generalized form, L sub n is equal to n over 4 lambda, but my n's, the things that were over 4, were only odd integers. So my n's have to be 1, 3, 5, etc. We call this an odd function because the n's are only odd numbers. And this is going to be the basic equation you're using in lab today. Just 2 more slides before I get to what we're going to do. This one here is showing the equation. Wavelength is a function of length, or frequency as a function of the velocity of the wave and the length. What we're going to do is essentially what's shown in this picture. We're going to take a tube and fill it with water. Now I have up here a nice little beaker. that you can fill with water. I brought a bunch of graduate cylinders you can use so everybody doesn't stand up here and wait for it. What you'll need to do is first fill this up with water. It takes a lot of water. Now, we don't want to spill water all over the floor, have somebody slip and have a problem. So I have these basins for you to put these in so that we'll keep the water contained. When I fill it up, I'm lifting this up just a little bit so it's not sitting on the bottom. I'll actually show you why you should do that by not doing it. So here I'm filling up without lifting. It's all the way up to the top in the center, but it's down there near the bottom and the outside. I lift it up and they'll equilibrate. You notice the oscillation, which is cool. But if I had it lifted the whole time, I could have just filled. There we go. So I filled this thing all the way up. I'm now ready to do the experiment. Now for the experiment, can you help me, Tori, please? Tori's job is ever so difficult. Hold that so it doesn't fall. I'm going to grab a tuning fork. I'm going to grab one that's a small one. Please don't hit the tuning forks on hard things. So don't hit them on people's head. Don't hit them on the desk. We have rubber stoppers because it kind of hurts to bang it on your finger. So I'm going to bang on the rubber stopper. Hear a note, right? Bring it up to my ear, nice and loud. Put it over here. I'm going to raise this until I hear resonance. Here? None? There? So when I get that resonance, then I have to need to have the meter stick and measure the height from the water level to the top of this. So this is where things get a little more complicated for Tori's position. Instead of just holding like I told her initially, I'm going to go ahead and look at it. I'm going to have her hold it something like this. So the middle finger and the thumb are holding the main tube, and then this index finger can come down and clamp if necessary. Then I'll raise it up and I'll say, there! And then she'll just clamp it with her index finger to hold it at that height. Got it? So, there's my first one. I'm actually doing that. There's my second one. Stop it there. Okay, so she's holding it there at the second resonance. Now you need to do all of them, not just start at the second one. So at the second resonance, I now take my meter stick. Remember, the ends are not calibrated, so it's bad form to use the end, although it's kind of hard to make these measurements. And then I measure where the water level is. I put 10 on where the water level is, and with this meter stick, it definitely works better to go like this. Put 10 where the water level is, and right now I'm being sloppy, and then I measure where the top of this is. You can't simply hold your meter stick the same place each time, because notice what happens to the water level when I raise it. It goes down, right? So you're going to have to move the meter stick each time. At one point I thought, gee, wouldn't it be smart for me to just, take these on? Nah, I really wouldn't. So you're going to be finding each one of the resonance position. So 1, 2, 3, 4, 5, and it's still well in the water, so I have more to go. For the small ones, they got the frequency stamped on them. This is 1024 hertz. You're going to have lots of resonances. For the longer ones, you'll have less. Now what you need to do, you can have a group with anywhere from, has to be at least 2, up to 4 in your group. But each person has to choose one different frequency tuning fork. Don't have everyone in the group grab a tuning fork at the same time, because we don't have enough tuning forks for everyone to grab a tuning fork. Don't grab the longest ones. They're supposed to have tape on them so you can't see what they are. They're supposed to be unknowns. But there's plenty for each group to grab one, have one person do it. Now when I say one person do it, I mean, for instance, when Tori and I were working, I was the one that was identifying this is where resonance is. And then I was the one that was measuring the height. That's my data. Then when it's Tori's turn, she gets a different tuning fork. I hold it. She determines where the heights are. She marks it up. After you have your data, then you're going to calculate what the wavelength was, and using that wavelength and the frequency that's stamped on the tuning fork, determine what the speed of sound in air is. Using the temperature, you'll get a theoretical speed of sound in air and find the percentage error of difference. So you need to do this with you need to do the calculations with both your date and your partner's date. And that's it. Yes, Sade.
Question, we don't have to write a hypothesis.
Correct.
Do we have a conclusion?
Yeah, you always have a conclusion because the conclusion is talking about what you learned, what went right, what could have gone better. And notice that sound is an important part of this. Getting away from other people helps the experiment be easier.
You said we can only grab one?
Well, just one per group. Yeah, because we don't have enough for everybody in the group to grab theirs. And yeah, don't grab the ones with the tape on them. Here, I'll set these aside.
No hypothesis or test.
Correct.
Okay.
We don't want to use these.
No, you can use any of those. I took away the ones.
Do we do